Now we will extend the result from last lecture to a more general case. Recall that the transportation cost and the holding cost. Here is the case when the rent cost is much larger than the inventory waiting cost. So now let's extend it to the general case that the inventory waiting cost cannot be ignored. So we will introduce continuum approximation, or CA. So recall that in CA, we try to estimate the parameter based on an infinite homogeneous assumption. So similar ideas will be implemented here. To simplify our derivation, we introduce another notation as the density of the customers in the service region. And then we can have this term be converted into a similar form. And then recall that our total number of items is number of customers times the total demands. So we can write the first part, the transportation cost per item, and also in infinite homogeneous settings, load for each dispatch at each customer can be estimated based on the total demand divided by the number of dispatches. And then the headway will be the load divided by the demand rate. So this can tell us, so our transportation cost can be written as, so recall as the holding cost per item for this infinite homogeneous case, if we consider the two-sided holding cost. So the total cost is also an UQ form for the headway. And then similarly, we can estimate the optimum headway and the corresponding optimum cost. Let's further generalize the result when pipeline inventory is not ignored. So previously we assumed that the pipeline inventory is neglected, and then we can guarantee that the capacity of the truck is fully utilized. But now when we consider the pipeline inventory, as we mentioned, we may not fully use the truckload. So in this way, the Vmax will be greater or equal to the number of stops times the load for each destination customer. Remember, the pipeline inventory cost for each item is related to the travel time during the transportation, TM. In our case, if we consider a tour from the depot to several locations and then go back, let's see the D will be the total distance for this tour, and then the speed of the vehicle is S. And also for each destination, the truck will stop, either load or unload the item, so we will consider stopping time. So in this case, our TM can be estimated by the half of the total time. So here the half means the waiting time for the first item is relatively short, but the waiting time for the last item is very long. And then the total travel time is D divided by S plus the total number of stopping time. So we consider the average of this total travel time as estimated waiting time for each items during the transportation. So now let's estimate the distance for each tour. Recall that we need to have a line haul cost and also a local TSP tour. So we can have the pipeline inventory cost for each item, or we write it with the function of number of stops. Because our load is no longer Vmax, but is decision variable now, which is load of each destination times the number of stops. So we also need to revise the transportation cost term. So our Vmax will be replaced. So we call this motion cost. And we also have our holding cost. Recall that our headway times the demand rate equals to the load for each destination. Hence, we can replace all the headway decisions by load, and then we can give the total cost expression. So we combine the three terms for each item, pipeline inventory cost, motion cost, and the holding cost, can have a relatively long total cost expression. So this is a too long expression. Then we can define some additional variables and then simplify the expression. So here alpha 0 equals to this constant term, alpha 1 this term, alpha 2 this term, and alpha 3 this term, and alpha 4 this term. And then we have the objective of the total cost. We want to minimize our total cost with respect to our number of stops and then the load at each destination. Remember, we have a constraint. And also we need to guarantee the number of stops is greater than 1 and smaller than a certain threshold if you want to guarantee that the number of stops is limited. So in fact, this is an optimization problem with two variables, ns and v, and then with some constraint. So let's see a special case when alpha 3 is very small. In fact, that indicates our pipeline inventory is small. And then in this case, we do not need to worry about this term. And then we try to minimize the total cost. So our number of stops will be optimized to be as large as possible. And then we have a binding constraint. So that means as large as possible will equal to Vmax. And then this reduced to our previous solution. In this case, we can observe this EOQ form of the decision on the headway or on the load. So in a general case, when alpha 3 is not 0, this cannot be ignored, then the problem structure becomes a little bit complicated. So here we can give you some hint of solution. So first, we will consider alpha 1 and alpha 3 terms and optimize it over a number of stops. So if the number of stops can be taken, then the objective is optimized. So this gives us, and also because, so we can have the condition that number of stops can be the inner point solution of EOQ. That means we have the range. Here we can see this is a one variable function on V, and also it has kind of a two trend. The square root of V inverse and then the V inverse decreases as V increases, indicates a trend in this way, and then V indicates an increasing sequence, trending this way. So the combination of these two factors will also lead to some Nike shape curve, and then there will be an optimum solution, although it's not very easy to get, but we can numerically find it. And then in this case, we have a range on V. Given on the range on V, we will get optimal solution either on the boundary or on the EOQ point. When the pipeline inventory cost is huge, and then it cannot be ignored, so we will typically consider a inner point solution for this optimum V. This can be denoted by V star. If we mathematically derive it, that indicates the first order condition over V. So we can give the first order condition. On the left hand side, this is a monotone function. So we can plot the curve and then find the point easily. Here we skip this solution process. This can be done numerically. So in this end, we can optimize our objective based on V and number of stops. This is for a infinite homogeneous problem. For a general problem, we may have different parameters over the space. For a certain range and a certain time point, we can have its corresponding infinite homogeneous problem, and then our solution will be given at each point by the corresponding optimum solution, and then the total cost can be estimated over the entire planning horizon, and then from 0 to Tmax.